Okay, so we got four categories: Department A, Department B, Department C, Department D. So we call this categorical or qualitative variables. Variable. This is one type of variable, the category, the department. So we either should use a bar graph or a pie chart. There's a few others, but those are the only ones we've introduced here. So let's see, what's our goal? A bar graph would be good if we really want to see which department was the best, because bar graphs can show us one is a little bit taller than the other. Pie charts are not good for that purpose because when you look at a pie chart, you can't immediately tell just by the graphic which one is bigger. It's hard to see which slice is bigger. So the primary goal is to identify which departments are performing the best. So we want to know which one is highest. That means a bar graph is more appropriate than a pie chart here. So to make a bar graph, make sure to start it at 0 on the y-axis. Otherwise, the size of the bins, the size of those rectangles, isn't going to accurately represent the relationship between Department A and Department B. And so it looks like we're around 500, so I'll go up by hundreds: 100, 200, 300, 400, 500. So Department A is, here's 600, oops, 500. So Department A is about a quarter of the way up between 500 and halfway between 500 and 600. So here's the halfway point, 550. So Department A should be somewhere right around here. I'll put that marker so I know how big to make the size of my bin. The other thing with bar graphs, make sure they don't touch, because categories are distinct. So we make them distinct by making them not touch. Make sure they have the same width too, so we don't mislead our reader. And Department B is 509, so that's just a touch over the 500 mark. So if I was to make a sketch, it would look like this. Nowadays, we just have technology that makes these graphs for us, right? But the big point of this question is knowing that a bar graph is what you want to make instead of a pie chart. Okay, 100, 200, 300, 400, 500. So 456 is a little bit over the halfway point. So for C, I'm going to make my bin right here. Then D is right at the 500 mark, maybe just a touch below. So D I'd do over here. Okay, so the bar graph lets us know all the departments are pretty close. Percentage-wise, they're really not that far off from each other, but A leads by just a bit. Okay, question 2. So this is quantitative data, numerical variables. A numerical variable, I should say. Well, no, there's two variables. This is a variable. This is a variable, so plural is correct. So it's numerical, so that means either a histogram or a box plot are the typical choices. Okay, so a histogram is good for showing how the data is spread out. Well, I guess a box plot does that too. So if you know it's quantitative, you'd want to make a histogram if you have just one variable you're trying to graph. You could compare two different histograms. Like this would be a histogram and this would be a histogram. Histograms are kind of like bar graphs, except the bins touch, because the scale is 0 to 10, 10 to 20, so they touch because they intersect with one another. But it's hard to do. If I made this histogram over here and if I made this histogram over here, it's hard to compare the two groups, right? You'd have to look back and forth, back and forth. A box plot is better because we can stack the box plots directly on top of each other. Here's roughly what a box plot looks like. Line for the median, and then we could stack this other one right underneath it so we can compare them. Okay. So this data set has a bit more spread, it seems, except for the middle 50%. But the highest values over here, lowest values over here. We can stack them right on top of each other and it makes for easier comparisons. So it looks like we want to compare the two locations. So a box plot is the appropriate choice for this problem. Okay, so to make a box plot, what you want to do is find your 5-number summary for each of these. Or use technology, okay? The first number is the smallest number, so 860, 804, 802. 802 is the smallest number. The 5th number is your highest number, so it looks like 990 is our winner. The middle number in your 5-number summary is the median. So to do the median, you've got to list them from least to greatest, but this is why using Excel or something like that is a lot easier. When you use technology, you can do it way faster than what we can do by hand. So I'm listing them from least to greatest. Let me scratch them off as I use them. 858, 860, 892, and 990. And to find the median, you scratch off the first and the last at the same time. First and the last at the same time. First and the last at the same time. So here's our median, 858. And then to find your Q1 and your Q3, that's what these last numbers are in the 5-number summary. These are like the medians of the lower half and the medians of the upper half. We call them the first and third quartiles. So here's our median. If we actually have a median, if there is a true middle number, scratch it out and take your lower half. Find the median of the lower half. Scratch off the first and the last at the same time. So 804 is our median of the lower half. And then do the same thing up here. Scratch off the first and the last. 892 is your upper median. So we call that Q3, the third quartile. So that's our 5-number summary. So we can use that to make a box and whisper plot. What you'd want to do is make an x-axis. Note where your smallest and largest numbers are. So I need to start at maybe 800. I'll go by 50s because that's 850, 900, 950, 1,000. You don't have to do it that way. You could go by 25s. You just have more hash marks. That's fine. And so 802 is where we start making our box plot, and we make just a tiny line. That's called the whisker, because I need to stop at 804. When I come in contact with Q1, that's when I start making my box. And the box stretches from Q1 to Q3, so 892 is a little bit less than 900. And then 858 is a little bit bigger than 850, so we put a vertical line right here. Then whisker all the way out to 990. And that's it. That's our box plot. So it shows us that most of the data is around the 850 range, because 50% of your data is within this box. But there are some values that make our whisker stretch out here. So there's some things that are borderline being called an outlier. Okay, and then you do the same thing for this over here, but I'll try to keep this video short. And then you could just draw it on the same axis because it's still talking about the same units. So whatever this one looks like, maybe it's a way bigger box, I don't know. But draw it right on top. Okay, and that's how you can compare them. Okay, question 3 is quantitative. Question 3, we want to know about how spread out, what the distribution is, in other words, of inches of mercury. Does it have a fairly even spread? Is it mostly centered around one value with a few really extreme days? We can figure that out really quickly with a histogram. So histograms and box plots are the go-to graphs typically for quantitative variables. You'd want a histogram if you just got one. Probably want a box plot if you want 2 or more. Those aren't hard and fast rules, though. You can do whatever you want, but in general, the box plot's easier to compare them. So histogram for this one. Same type of thing. You probably want to list them from least to greatest. So smallest number here, 29.8, looks like a winner. I saw I had multiple 29.8, so I had one at the top, and another one. So I got 2, 3, 4 values at 29.8. So we got 1, 2, 3, 4, and then what's the next highest? 29.9. I've only got one of those. Super exciting stuff, huh? Putting things in least to greatest order. 30.1 looks like the next. Oh no, I have 30.0. Oh boy. What a real shocker. 30.0, then I had 30.1. That's gone. 30.2. I've got 3 of those. 30.2, 30.2, 30. 6.2, 1, 2, 3, and then two 30.3s. Okay. And so with histograms, you have to decide, just like with the other ones, your interval on the x-axis. It looks like 0.1. I went up by 0.1, and went up by 0.1, went up by 0.1. So I'll just do 29.8 here. This will be 29.9, 30, 30.1, 30.2, 30.3. And the y-axis on your histogram is the frequency. How many numbers do you have that fits in between these bins? So this one, because of the way the numbers worked out, they're really close. What happens when a number lands right on the edge? 29.9. Should I put that over in this group, or should I put that over in this group, because it's right on the line? So I think I'm actually going to change my x-axis just to make it clear, because a person that comes and looks at this histogram isn't going to know exactly where the next one is. It's just because this is a bit of a weird data set. Let's change it like this. Since we know going up by 0.1 was easy, since I know I don't have any 0.5s, I can make sure I don't run into that intersection by problem by doing 29.75. Wait, sorry, let's do 29. Yeah, 29.75. I went 0.05 less than this one, and then we'll go up by 0.5 each time. That was just my decision. You could have done 29.79 and then 29.89. That would be fine. Just something to make sure you know what to do with those numbers if they were to land. We want to avoid that problem of landing right on the edge, so that we're not sure which group they go in. And then we got 30.05. I'm just adding 1 each time. That's another big emphasis when you make these. You got to make sure the x-axis is consistent, or else you'll mislead the viewer. So watch out for that if somebody gives you a histogram, and if you see that they jump by 2, and then by 1, then by 2. Okay, so now we can graph between 29.75 and 29.85. We've got 4 numbers that meet that criteria. So 1, 2, 3, 4 on my frequency. Make your bin go that high. Then between 29.85 and 29.95, I've got this one, this one, this one, this. I've got 1 number, so I go up to 1. 30 is between these 2 numbers, so I've got 1 number that meets that criteria. 30.05 and 30.15, I've just got 1 number. I've got 3 30.2, so 3 numbers that fit in this category. Okay, so it's not often that we're asked to make a presentation where we have to graph data like this, right? A big takeaway from this lesson is to know how these are supposed to be constructed, because there's lots of advertisers, there's lots of people trying to convince you of something, and they can mislead you by making it look cool with a graph, but the graph is made incorrectly. So make sure that the x-axis is consistent. It's always going up by 1 each time, or whatever number they tell you. It could be a scale of plus 10 each time, plus 10, plus 10. If it's not plus 10 each time, if it's not plus a consistent amount each time, then you might be being misled. Same thing with the y-axis. You can't do 1, 2, 3, 4, 20, right? It's got to go up by the same amount each time. Okay, and then last one. These are categories, okay? I know we see numbers here, but fat is a category, right? This is not a number, this is not a number, and this is not a number. So these are like the frequencies, like how many calories that fit in here. We're trying to make a graph that to understand the portion of our diet that's fat, protein, and carbohydrates. I think that's the only way we can interpret this. If the question said make a graph to show where the majority of calories come from in this diet, that'd be a bar graph. But with diet, that's a classic example of where we'd want a pie chart. That way we can quickly see the percentages. Okay, pie charts, usually we do those with technology, because in the old days you'd have to get out a protractor. You'd probably have to do some trigonometry, I guess. I don't remember what we did a long time ago. Okay, and so you want to convert each of these to percentages. So the total amount, 2,200 calories. Um, so to find out the percent that was fat, what you do is you take the amount of fat, divide by the total, oops, and then times 100. So that's 27.27%. And then protein, 400 divided by 2,200. That's 18.2, we'll say. And carbohydrates, that's 54.5. Watch out for this rounding rule. When you round, you've got to make a decision on which place value to round to, and then you don't look at anything other than the digit directly to the right. So look, I was going for 1 decimal to the right when I convert it to a percentage. If I was to keep going, I could say, well, the 5 bumps this 4 up to a 5, and that 5 would bump this 5 up to a 6, but you only look at the digit directly to the right. 54.5, and that 4 is below a 5, so we round down. Okay. Okay, so this slice for carbohydrates should be a little bit bigger than half. Let's start with that. So this would be half. So I'm going to make my slice go a little bit down like this. And that's carbs. I'll just use C for carbs. Fat and protein make up the rest. I just want fat to be the bigger slice. You can see why technology is better. So if I was to go straight down, that would be about 25%, right? Because this is the halfway mark, and then cutting it into another quarter, that's 25%. So it should be pretty close to straight down, trying to make it go a little bit to the right. So that's fat, and then this would be protein. There's our pie chart, so we can quickly see calories come mostly from carbohydrates, with fat and protein a pretty similar percentage of the diet, fat being a little bit bigger. Okay, so this is the most important thing for this type of material, is to know how this is going to impact us. This actually happened at the school I was working at. They gave us this graph, and they said, look, if you use our product, your scores are going to go up. Well, there's a couple things wrong with that. Schools that can afford your product are probably just going to do better because they're able to either get more teachers, they're either able to be more competitive and hire better teachers, maybe they have better materials. There's a ton of different reasons why, other than your product making these students more successful. But in terms of the construction of this graph, if you go back and look at what we said about bar graphs, first thing I think I said was you got to start it at 0 on the y-axis. It starts at 50, right? So that makes it look like their program doubles the performance on this test, and it doesn't, right? So it went from 70 to 90 on this test, on this math test score, which is a great improvement. If the product's really making that improvement, that's great. But it's not by double. It's not. This one isn't half of this one. To calculate the percentage change, you take the amount you increase by, which is 20 points, divide by the starting amount times 100. So it's not increasing by double. Instead, the amount that we increased by was 28.6% roughly. So that's a misleading graph. Okay, and it happened too in my local town. There is a new town manager, and he made a graph to show revenue because he was trying to advocate for more spending, which is great. You know, revenue went up. Certainly, the town could afford to spend more money on making some improvements, but I looked, and the bar graph did not start at 0 on the y-axis, so it made it look like revenue jumped way more than it actually did in the previous year.